So, as you can see, the title of my talk has to do with damage-based capacity limit states, focusing on non-ductile bridge columns. I want to acknowledge my former graduate student, Joe, who pretty much did most of the simulation that I'm going to present here today. All right, in terms of the outline, I want to provide some background as to why we undertook the study. It has to do with a platform called ShakeCast that maybe some of you know. So the current version of ShakeCast uses some extremely old demand and capacity models, and Caltrans is in the process of coming up with what they call the next generation bridge system fragility relationships. So the main task here was to come up with what we call component capacity limit states. Because we do have a lot of work done on the side of estimating demands, but when it comes to looking at the capacity of existing bridge columns, there's still quite a lot of work to be done. And so I'm going to provide the conceptual basis for how we came up with our models, and then talk a little bit about ductility and damage-based models. So if you look at most of the work that's out there in terms of damage, is mostly ductility based. So if you have an estimate of ductility, you can come up with an estimate of damage. And then we kind of applied them to, actually here I'm going to focus a little bit on multi-column bends, but we did, carry out these studies on single column, 2-column, and 3-column bends. And some of the findings from the project. So starting off talking about ShakeCast. Okay, this is kind of a real near real-time damage assessment. So what typically happens, when you have an earthquake at some location, is that you get ground shaking data from USGS in near real time, about a minute or so, and then the shake map then provides the inventory of existing bridges around that area. All right, so so all the bridges in the vicinity of the earthquake is identified, and then then they go into these probabilistic seismic demand models to see what kind of demand some of these bridges may have experienced. And so the idea then is to associate those demands with likely damage. All right, so that Caltrans can then assign the resources accordingly to go to sites where you expect most of the damage to some of these existing bridges. So I should mention that at the time we started this project, Caltrans already had a fairly extensive project ongoing with Georgia Tech and Rice University at that time, also looking at capacity limit states. But they focused mostly on experimental data. So they had this large database of experiments done over the years, but mostly on single columns. And they tried to use that as a base of coming up with these so-called capacity limit states. So when I proposed this project to peer, I said, why don't we then, given the limited amount of data that's available from experiments, why don't we use our modeling tools and use simulation as a basis to generate a much larger data set to come up with these capacity models. Right, and again, so, like I said, there's limited experimental data, especially on older columns. And so, the need, therefore, to resort to numerical simulations. So currently, Caltrans classifies its bridges into 3 groups. They call them Era 1, which is pre-1971, and then an Era 2 when, you had, slightly more, when they revised some of their design guidelines, and that's Era 2, and the modern bridges are essentially what's called Era 3. So in this study, we focus primarily on the Era 1 columns, what I call non-ductile, existing non-ductile columns in California. Okay, and they are characterized by some, important, characteristics here shown here. You have transverse reinforcement ratio less than about 2.5%, and in some cases they even have lap splices at the base of the column. All right. So since this is all about simulation, we spent quite a bit of time trying to identify, appropriate models. So here I'm showing you how the typical columns were modeled. The main nonlinear element in these bridges are the columns themselves. Here I'm showing you a single column, but we use the same approach for modeling, the multi-column bends as well. So we had multiple integration points along the member. We had a shear spring as well as a bond slip, with a zero length section there. we kind of calibrated them to different, so we have different modeling approaches, and essentially we tried to approximate, what I would consider a more accurate model, which is a non-local model, which at that time my currently former graduate student was working on, and so we tried to, so we didn't use non-local formulations for these simulations, but we tried to use the existing model to come as close as possible to a non-local formulation. So the kind of material models we looked at were, of course, the confined model for concrete, and so we also looked at a strain penetration model, the column base to the foundation. The other thing we focused on also was the likelihood that bars, especially in these older columns, would buckle. So we also, on the compression side of steel, we also wanted an adequate rebar buckling model. And in terms of monitoring material response, like I said, so we used concrete O2 to represent both the core concrete and the cover concrete. And so we were looking at things like the onset of cracking on the tension side and the onset of crushing on the compression side. In terms of the steel model, we use the hysteretic material. Again, it's a little bit more convenient to use this, because you can, keep track of the initiation of buckling on the compression side, and of course bar rupture on the tension side. So the first thing we did, as with all models, is to kind of validate some of the modeling approaches using some experiments on non-ductile columns. So we picked 3 of them, tests done a while ago, but they all represented the kind of bridge columns that we were looking at, the so-called Era 1, with low transverse reinforcement ratio and approximately the same amount of longitudinal steel as well. All right, so looking at Era 1 columns, we looked at the entire database, the current inventory in Caltrans, and so what we found is that, typically you had diameters ranging from about 3 to 5 feet in length, and this is the percentage. So as this is about so we're looking at, the majority of columns having a height to depth ratio of about 4, and here is the distribution of the transverse to longitudinal steel ratios as well. So really the bulk of them, as you can see, lie around here. You have some outliers, and so our task was then to come up with a set of columns that would represent them. So we had the majority of them lie within that range, but we also had a couple of outliers. For example, we have here 5% steel, and also some transverse steel ratio going to about 0.5%. And again, so in addition to picking these, cross sections, we also varied the hysteretic parameters to give us, some more, additional simulations, so that statistically we could have some estimates of, what was happening. Now, another feature of the Era 1 columns is they have, Caltrans is a large, group of what we call wide sections. And so these wide section columns, when we look at the aspect ratio in the 2 dimensions, so these are essentially rectangular columns, but they are extremely wide in one direction. And so again, we tried to look at the characteristics of some of these sections, and we identified, a subset here. And here I'm showing you some of those columns. As you can see here, you're looking at, an aspect ratio anywhere from 2 to 3. So the depth in one direction is 33 feet, but it could be as much as 8 feet in the other direction. So this is what I mean by wide columns. All right. So once we've identified both a set of circular columns and rectangular columns, we proceeded to analyze them first under cyclic loading to come up with so-called our damage parameters. So we subjected them to single cycles, per drift, 2 cycles and 3 cycles. And some of the things we monitored, these are for the circular sections and these are for the rectangular sections. We obviously monitored the strains in the cover. We also monitored the strains in the core at different regions. And again, these are some details and similarly with the rectangular sections as well. So this provided us the basis. So we essentially were using strain measurements in our fiber models to kind of come up with our damage estimates. So at that time, Caltrans was interested in 7 damage states, all the way from no damage or negligible damage, all the way through collapse. And so in terms of, in the first phase of the study, we actually looked primarily at ductility. So we were correlating our damage states to certain ductility levels, and at the same time monitoring the strains, like I said, both in the concrete, and in the steel. And so here, what you see is a summary of these 7 damage states for both wide section columns and circular section columns, as a function of ductility. Okay, and what you'll see is very interesting is that the wide section columns actually performed slightly better. So we're talking about for the same, for the same damage state. So if you pick a damage state down here, like damage state 6, the ductility, for example, at you'd reach a damage state 6 for the wide column much earlier than you did for the circular column. So clearly, circular columns were performing better than the wide section column. So this is one of the early findings from our study. But then when we started to go to from cyclic loading to earthquake loading, what we found very interesting was that the peak ductility demand did not give us a good estimate of the damage in the section itself. So this is from an actual experiment where, following the extreme, displacement ductility, for example, if you look at seismic loading versus the mean of cyclic loading, we found that if just focusing on the peak ductility did not give us a good estimate of the actual damage in the section at failure. And as a result, we decided to, for example, here you can see here, the peak displacement at all of these damage states 5, 6, and 7 happened at a ductility of 4 because, you achieved that well before the section actually failed. All right, so we spent some time coming up with a damage-based model where we're looking at, damage in the concrete, where we used, a kind of a linear relationship up to the peak, and then as it starts to soften, we use a different relationship to indicate that, damage would progress at a much higher rate in the concrete. And likewise, for the reinforcing steel, we mostly relied on, on a fatigue-based damage model. And we use weighting factors without getting into too much detail about the modeling itself. So we're monitoring damage in the fibers in both the, the core concrete and in the steel, and we used weighting functions to come up with a so-called overall damage index, for the column. Now, in addition to just monitoring damage, we also focused on specifically on the buckling in the reinforcing steel, which, as you realize, is history dependent. So if a rebar experiences tension first before it goes into compression, it's likely to buckle sooner. So we monitored. So we came up with a fairly detailed approach to monitoring buckling, and as a function of the cyclic history. And so here you see our final, description of the different damage states from damage state 1 through 7. And here is the description of that. So, at damage state 1, we're just looking at basic, simple cracking in the cover, which is a kind of a negligible damage state, all the way to collapse. All right. And so, for example, the important things here for, is damage state 4, which is when you see the initiation of bar buckling. And then when you see an exposed core or the first rupture of a bar, we get into extreme, damage states followed by multi-bar rupture. And so we were able to calibrate all of these, just looking at the strains, in the different fibers in the cross sections. Okay, and so we calibrated these damage states using, again, experimental data. These are cyclic experiments done, followed by, we also looked at a shaking table test that was done here, here at Berkeley. And so again, we were able to reasonably calibrate, several of these damage states, because in this shaking table test, for example, in addition to spalling, so we do have data on bar buckling, we do have data on multi-bar rupture, and of course there was no real collapse in this particular column, but as you can see, at least the early damage states all the way through buckling, and the multi-bar rupture was captured quite reasonably. Okay, so moving quickly then to the the analysis itself, we looked like I said, we looked at single. Thank you. So like I said, we looked at single column bends, 2 column bends, and 3 column bends. In all cases, what we did was to make sure that the lateral capacity of all of these were consistent. All right. So we're looking at all of these bridges designed to approximately the same hazard or to the same lateral capacity. Okay, and this was of some importance to Caltrans at that point in terms of looking at a single column versus a multi-column bend into whether a multi-column bend would provide some additional safety. So we looked, so the ground motions we used in this particular study were for those of you familiar with the FEMA 695 ground motions, that's kind of grouped into pulse-like and non-pulse-like motions. And these are some sample, IDA simulations looking at single column bends and at 3-column bends. Okay, so like I said, we also did them for multi-column, for 2-column bends as well. I'm just showing some sample results here. So this is the probability of exceeding a certain damage state. So this is damage state 6, as a function of the intensity measure, which in this case we selected, as SAT1, which is a reasonable intensity measure for bridge columns in California. And so I think I'm showing the same bridge here, pulse-like. I think this is a different damage state. Should have been a different damage state, but I'm showing the same one here. But we looked at different damage, the likelihood of reaching different damage states as a function of the intensity measure for pulse-like and non-pulse-like motions. And clearly we see that pulse-like ground motions do result in higher damage. Here I'm looking at single, 2, and 3-column bends. And if you look at lower damage states like DS2, which is a lower damage state, you find a fairly good separation between a single column, 2-column, and a 3-column bend. But as you go to higher damage states, for example, damage state 5, you realize, what we found is that 2 and 3-column bends had pretty similar responses. So there was a, fairly noticeable difference between a single column and, or 2 or 3-column bend. But going from 2 to 3, the response was not that much different. All right, to quickly conclude, just a few statements. First of all, we found that using purely a ductility-based limit states is not necessarily reliable when you're looking at earthquake loading. And the so-called damage-based limit states that we came up with were, fairly independent both of the failure mode and the loading protocol. So talking about failure modes here, they were mostly flexural columns, but we did look at shear failure as well, which I haven't presented here. But we're looking at things like the initiation of bar buckling and multi-bar rupture and so on. We found that the damage-based limit states, performed much better than just looking at peak ductility. And like I said, the reason we looked at multi-column bends was to look at redundancy provided by multi-column bends, indicate that, the 2-column bends provided, the additional margin of safety for all damage state, but, you would get no further enhancement in going to 3 or bends with more number of columns. So some of the things that we're still kind of looking at is to refine some of the damage model for early damage states, because we find it, it does fairly well when we get to buckling and bar rupture, but we're looking at early damage states when we're just looking at what's happening to the concrete. There's still a little bit of work to be done. And something else that I'm doing with, I know that my colleague here, Farzeen, is doing some work at UCI also on damage limit states, and so we're trying to look at some of his findings from that study as well. All right, and finally, just I need to acknowledge, Cliff Robley at Caltrans, who initiated a lot of this work with the shake cast models, and the group at Georgia Tech, who also, we collaborated on a few of these things. Okay, with that, thank you very much.